This is CSaP's Science and Policy Podcast from the University of Cambridge, where we're bringing you the latest evidence and expertise to improve public policymaking.
How is climate change affecting the most extreme and remote habitats on the planet? The concentration of CO2 in the atmosphere is higher today than at any time in at least 800,000 years. Even if every country meets their commitments to reduce carbon emissions rapidly and significantly, as set out in the Paris Agreement, some amount of global warming is inevitable. What will the consequences of this warming be for Antarctica and the oceans? Most of the excess heat from greenhouse gas emissions is taken up by the ocean. The ocean might feel remote and unimportant to daily life, but the reality is that there is a close connection between even the very depths of the ocean and the rest of the climate system. Europe's temperate climate is reliant on the Gulf Stream, the conveyor belt of the Atlantic Ocean, which is itself part of a global-scale system of ocean currents known as the Meridional Overturning circulation. Extreme weather earlier this year, including record snowfall across Greece and Spain, has been directly linked to a weakening of the Gulf Stream. This weakening is set to intensify as the oceans continue to warm. The separation of an iceberg the size of Greater London from the Brunt ice shelf in Antarctica made global news earlier this month. Many people are by now familiar with the idea of climate tipping points, transformations which are irreversible on human timescales. The loss of Arctic summer sea ice has gained widespread recognition as one such change. Does Antarctica have similar tipping points? How and why are the changes at the South Pole different to those at the North Pole? And how do we collect the data needed to answer these questions? Satellites are a large part of the picture here, having dramatically improved our ability to observe and measure ice and the oceans at global scales. Rocket launches are far from green, however, so how do we balance the need to put scientific instruments into orbit with the knowledge that doing so will release tons of CO2 and aerosols into the atmosphere? Within this podcast episode, we will consider these questions and more through the lenses of science and policy. We'll look at the consequences of climate change, efforts to improve scientific understanding, and proposals for mitigating the worst effects of global warming.
Hi, I'm Rob Doubleday, host of CSaP's Science and Policy Podcast. You've just heard from Anthony Lindley, a policy intern here at CSaP. Throughout today's episode, we're discussing climate change in the Antarctic, in our oceans, and exploring how scientists are using space to study the changing climate. In today's episode, we're joined by atmospheric physicist and former co-director of the Grantham Institute at Imperial College, Professor Joanna Haigh, oceanographer at the National Oceanographic Centre, Professor Penny Holliday, and Professor John King, an atmospheric scientist with the British Antarctic Survey. And today we're going to be talking about space, oceans, and Antarctica as these places relate to human understanding and human impact on climate and how it's changing. So, Joanna, if I may start with you, are we right to think that our understanding of climate change is significantly shaped by what we've learned from space?
Yes, the measurements that are being made from space have been hugely helpful. If we go back to the late 1970s when the first weather satellites were launched, and they revolutionised numerical weather forecasting by providing data over the globe twice a day and sending it back so that the meteorologists could create maps of what was going on in terms of temperature and clouds and humidity. Now, of course, climate is a much slower moving thing than weather, and it's usually defined as being a 30-year average, or at least that's representing the climate. So now we've got more than 40 years of data from satellites where you can begin to see how the atmosphere and the climate are changing. So if we look at what's actually being measured from the satellites and how this helps us understand the climate, the World Meteorological Organization has defined 54 essential climate variables. And don't worry, I'm not going to tell you what they all are, but they cover the atmosphere, the oceans, land and ice. And they look at the physical properties. So as I mentioned, temperature, pressure, chemical properties like the composition of the atmosphere, and biological properties. So Penny will talk more about the oceans, but we can look at ocean color and look at the state of the oceans and this sort of thing. And so this is a fantastic set of data for looking at the state of the climate, not only in terms of an average, but also its variability. So we can see how it changes from year to year, and also patterns of climate across the globe. You can't see these from the ground, or it's very difficult to establish. I mean, in the context of climate change, of course, we've got the global mean surface temperature records that go back for over 100 years, and they're from people having thermometers over the globe, and they have to be very carefully calibrated and compared and all the rest of it. And they've been hugely useful in seeing what climate has changed like over that period. But if we're looking now at the impacts of climate change and what is happening on the Earth, the satellite data are absolutely indispensable.
Are we seeing a change in what's possible? Are we getting better data over time?
Yes, so that there's various things that are happening better. One is just the quality of the data. So we have data that are more accurate or more precise with better instrumentation. But we also have better coverage in terms of spatial covering. So if we're looking at, for example, biomeasures on the land surface, we're now down to sort of tens of meters. We can see variability, which is hugely useful for looking at forests and that sort of thing. So we can see better space. We can see, individual weather patterns. Individual clouds gets a bit, more tricky, but certainly cloud patterns and weather patterns and things like the El Nino Southern Oscillation, which is hugely important for climate. We can now see how that impacts sea surface temperatures in the Pacific and the precipitation patterns and all that sort of thing. So that's the spatial sampling, but also the temporal sampling. So with more satellites and different sorts of orbits, we can sample the climate variables more frequently, and that, of course, gives us better measures of climate variability.
And Penny, if I can turn to you, when it comes to understanding what's going on with the oceans and how this kind of relationship between oceans and climate change, how much can we understand from space and how much really relies on being able to sample, collect data from within the oceans themselves?
Yeah, so there's no doubt about it that the data that we collect from space, this remotely sensed information, gives us an amazing global view of some of the things that Joanna was just talking about. We get this incredible spatial distribution. We can see most of the globe in 10-day cycles. So we get this amazing global cover, but it can be at relatively low resolution spatially. We don't get all the details of all the small scale features in the ocean from them. And we also don't always get enough information about what's happening below the surface. So changes in the surface are a kind of an integrated effect of what's happening below the surface. But sometimes we need to know more details about what's happening underneath the surface of the ocean to be able to see what changes are taking place in the ocean current and their impact on our climate system.
So how do we know what's going on underneath the surface? What techniques are used?
There's a couple of things that we're really interested in knowing. We want to know what the temperature of the ocean is everywhere, because one of the things that most people will be familiar with the idea is that with climate change, the ocean is warming. Something like 90% of the heat, the excess heat that we've been accumulated in the Earth system is actually stored in the ocean. We want to know where that is, where it's distributed, how that heat is moving around. And in some places, this increase in heat is extraordinarily large, actually. Places are suffering from these marine heat waves where temperatures are exceeding anything that's ever been seen before in the record. And that has really devastating impacts on local ecosystems, for example. So a lot of the way the heat is distributed around the ocean depends on the ocean currents. We have these very large-scale global patterns of ocean currents, which can take heat from the warmest areas and redistribute it to the cooler areas. There's something called the Meridional Overturning Circulation, or MOC, we like to call it, because otherwise it's a bit of a mouthful. The MOC can take heat from the sort of tropical regions and carries it northwards in the Atlantic Ocean, and that helps give Europe its nice sort of temperate climate. It's only recently that we've been able to directly measure what that MOC is actually doing. In 2004, the UK and the US set up a system of measurements, which is very engineering heavy. What we have to do is we take ships out and we leave instruments in the ocean. The ocean can be, 4 or 5 kilometers deep. So you have a sort of a string of instruments that's tied to the seafloor by an anchor and is held upright with flotation units. And you put instruments at various places along that mooring, that wire. And by stringing a series of these moorings across the ocean, you can measure directly how the ocean circulation is changing, what the temperature is doing, what the velocity of the currents is doing. And you can actually quantify how much heat is being transported northwards through the Atlantic Ocean. And what we found through this experiment is that the rate of this overturning circulation varies much more than we thought it would do, actually, and much more than we can detect from just surface measurements. So this was really interesting to us. And it's not just interesting to scientists, it's super important, because getting the representation of this ocean circulation right in climate models is an absolute prerequisite for getting climate projections to be accurate.
That's interesting. So there's much more variability. That's during the course of the time that these instruments have been active. Do you have any sense about whether that variability is sort of normal? Do you have any indirect ways of getting at how these currents have changed over time? Or are you only really able to speak with confidence about data you've managed to collect more recently? I guess we're interested to know whether we're at a position of change and tipping points that are going to be unpredictable, or whether science has got some handle on how these sort of ocean currents are behaving over time.
Yeah, so what we do is we use a combination of these observations and models and proxies. So proxies are sources of information from, they might be sediments in the ocean, or they might be ice cores, which give an indication of how climate has changed over longer periods of time. So we're not exactly able to completely reproduce what the overturning circulation has been like over 1,000 years, but we can get some idea as to whether it was working sort of at a stronger level or a weaker level. And then we can use the combination of the models and other observations to say, well, this variability that we're measuring over the past 15 years or so, how can we explain that? What is really influencing that? What's causing those changes? And so we can unpick things like a seasonal cycle in the ocean circulation, or a year when the change in the atmospheric circulation in the wind pattern generated a speeding up or a slowing down of the overturning circulation. We can use a combination of all these tools to understand what that variability actually means. And the reason that's really important is because what we absolutely must do is be able to reproduce these changes in the models that we use to create our climate projections. So one of the things that we aim to do with these experiments where we put instruments in the ocean is to really test our understanding of how these processes work. Because if we don't get them right in the models, then we'll have less confidence in the skill of the projections for future climate.
How good are our understandings?
Well, they're getting better all the time.
I want to turn back to Professor Haigh and thinking about space. You've talked about how important Earth observation satellites have been in helping develop our understanding of climate and Earth systems. But interested in now, obviously, the commitments to net zero, the commitments to mitigating climate change. I'm interested in what role space can play in tackling the consequences and reducing the risks of climate change.
There's several ways that this can come about. In terms of mitigation, it's quite important if you want to site, for example, wind turbines or solar energy systems, to know what are the conditions around the sites and whether they'll be best situated to provide those sorts of energy sources. So you can get good data on that, whether you need to have what the spacing of the wind turbines needs to be and how you line them up and that sort of thing. It would need to be based on knowledge about local climate situation. Also, of course, very important is looking at disaster monitoring. So we are aware that with climate change, there's going to be more extreme events, and particularly heavier storms and probably more coastal flooding. And so if we have monitoring from satellites, we can see these happening, but we can also predict, if we've got the information coming, we can see that it's more likely to happen and know where to invest in prevention. So, flood defences or coastal protections, for example, to try and mitigate against the worst effects of climate change.
People are concerned that, what if our attempts to transition to a net zero society, are too slow? Or what if there are sort of unpredicted risks emerge that come on quicker? Do we need a sort of plan B that geoengineering represents? And if so, is space going to be the site at which some of these options become possible?
Yeah, so the term geoengineering is used to cover quite a wide range of techniques from essentially, artificial trees that are sucking CO2 out of the atmosphere. And you can't really say much wrong about that, except can they do it at scale, and what are you going to do with the CO2 once you've got it solidified or whatever, and carbon capture and those sorts of things. And that's on the carbon side, which you might say is sort of correcting the evils that we've done in the first place by putting the carbon into the atmosphere. There's an alternative set of geoengineering proposals, which are generally referred to as solar radiation management. And the idea here is that because the energy driving the climate system is coming from the sun, if we want to reduce global warming, we just try and stop some of the energy coming in from the sun. And again, there's a range of different ways that you can do this. One of the ways is being proposed and is being investigated is to put a whole load of little particles up into the stratosphere, and they float around there for months or years, and they're reflecting sunshine back to space and thereby cooling the planet. The trouble with solar radiation management is that it's not addressing the problem. Whereas solar radiation is predominantly absorbed near the equator, greenhouse gas warming is spread more over the globe. You've not got the same heat balance as you would have in the natural atmosphere. And computer models have shown that actually this means you're going to have changes in the hydrological cycle, in particular stronger precipitation in the tropics, even if you can constrain the global temperature rise to zero. So you're not getting back to a non-changed climate, you're getting back to a different climate, but with the same temperature. And also you're not correcting for things like ocean acidification that goes on with the increase of CO2 in the atmosphere. Other problems with geoengineering are around the moral hazard, which means if governments or policy people think that there's a correction to the greenhouse gases, then there's less pressure on them to do something about it, because all they need to do is buy some high-tech geoengineering kit, and that'll take the pressure off the fossil fuel industries and things. So my overall perspective, certainly of solar radiation management, it's just not a way to go. Actually, why did I get into this? Oh, because the space thing. One of the things that's proposed is giant mirrors in space, which are going to reflect sunshine back and thereby cool the planet. So that's got all the problems associated with other solar radiation management techniques, plus the fact you've got to get a load of little reflectors up to represent these giant mirrors, and you've got to keep them up there. They won't stay up there forever. So, yeah, science fiction, really.
So it's interesting you're saying, so there are people who take a different view to you. There are people.
Oh, absolutely. No, there's very good. I mean, on the space reflector, big mirrors in space, there's a technological outfits in the United States developing how these were done, and how many little mirrors you need to put up every year, and how many launches of spacecraft you'd need to keep them up there, and what's the CO2 effect of those launches and that sort of thing. The more likely to be implemented one is the particles in the stratosphere, and this is being heavily investigated. They're about to do a simulation of stratospheric reflecting particles by launching them off a space place in Sweden to see how they work in terms of reflecting sunshine back to space. And I think the harm from that is mainly this moral hazard. It's an excuse. Now that the proponents will say this will buy us time while we get our act together and get rid of the CO2 emissions.
Or possibly an insurance policy if our best laid plans don't work out.
Well, if it's maybe too late by then, there's a carbon budget. If we exceed a certain amount of carbon emissions, we will not keep the global temperature rise to less than 1.5 degrees. There's an absolute amount of CO2 we can emit. And if we go over that, there's no way we can keep it to 1.5 degrees unless we start doing negative emissions and sucking CO2 out of the atmosphere. And in that case, solar radiation management won't help. And you'll have to keep it going and keep it going and keep it going forever, or else, you'll be back to a high CO2 and warmer climate. So I think it's a dangerous pathway.
You mentioned that people are studying the impact from space launches, exploitation of space in terms of emissions of greenhouse gases. Is this an area that we ought to be concerned about? I mean, is space exploitation going to be a significant contributor to greenhouse gas emissions?
So that's a very interesting question, and something that we'll have to keep our eye on. I mean, in what's going on at the moment, for example, if you get one of Elon Musk's huge SpaceX rockets, one launch of that will be about 1,000 metric tons of CO2, which is the equivalent of 200 car emissions for a year. But the current global greenhouse gas emissions are about 50 billion tons. So that's 50 million SpaceX launches, if I can put it in that context. So you might think that's tiny and not really to be concerned about. However, if we consider that Elon Musk is planning 12,000 satellite launches in the next 7 years, and there's competition with Jeff Bezos and Richard Branson for commercial space flights, and any number of smaller companies all getting into it as well. I think we're going to have to start really worrying about the greenhouse gas emissions of the space sector itself. Now, there's work going on to try and create green rocket launches and this sort of thing. In fact, the European Space Agency, their next Ariane spacecraft design is designed to be carbon neutral. It's going to burn biomass methane by 2030. So that's a good way to go. But you do have to worry about black carbon as well as the greenhouse gases, as well as carbon dioxide. So there's all sorts of issues. And I think the problem is only going to get larger.
Thank you very much. Penny, I mean, just on that briefly, does the National Oceanographic Centre have to think about its own carbon footprint? Because, ships are emitters of greenhouse gases. How do you think about the kind of the balance between the importance of the scientific work and the emissions that are entailed in carrying out that research?
Yeah, it's definitely a major consideration for all oceanographers, I would say. We are also all working towards a net zero carbon future as well. And the carbon emissions associated with our ocean measurements and the models that we run as well are all, taken into consideration. And we are looking for ways to use technology to reduce those carbon emissions. So, for example, some measurements that are presently made by ships will be made by autonomous vehicles in the future. So you can send ocean robots out. We're already using quite a lot of robotic technology, as you talked about in your recent podcast, to measure different aspects of the ocean. And I see that increasing as time goes by. And there's also, of course, developments in shipping technology, which will hopefully lead to ships producing fewer emissions themselves. There will always be, I think, a need for ship-based observations of the ocean. And again, in the grand scheme of the global emissions, they're probably quite small, but we are certainly working towards a net zero carbon future for all of these reasons. We want to be part of the solution and not causing the problems ourselves.
And if I may just ask one final question, Penny, it's around the sort of role of oceans in mitigating climate change, and particularly this question of blue carbon. What are the sort of research questions about the likelihood that this is going to be an important part of our response to climate change?
Yeah, so the idea of blue carbon is all about restoring some of our sort of natural vegetative ecosystems around coastal areas. So you might be, depending on what your sort of natural environment was before human exploitation, you might be restoring mangrove swamps or tidal marshes or seagrass meadows. And the idea is that those ecosystem environments will be absorbing and storing carbon from the atmosphere, and they'll also be beneficial for biodiversity and possibly fisheries as well. And they will also have the impact of protecting people on land from the worst of the storms and the sea level rise that's currently happening already. So there's a very strong persuasive argument. Sounds like a much more simple and attractive than Geo Engineering, which is fraught with danger. So it has a very strong appeal. And I guess the challenge is going to be around deciding where is the appropriate place to be developing these areas, how to monitor them, how to make sure that they are doing what we want them to do, and also really sort of quantifying the difference that it actually makes to the climate system.
Because I suppose that, and that may be where space comes in again, is that as we come to these measures, we will need to have systems for sort of monitoring and validating the kinds of interventions that we make. So I guess that's where oceans and space can be working together again.
Yeah, I think that's right. I do think the interface between the land and the ocean can be a tricky place for satellites to measure. That may be a challenge that perhaps Joanna can comment on, but it's that the change between the ocean and land, is hard for satellites to really be able to cope with, because each satellite can be measuring quite a large footprint of surface area, and being able to distinguish between those different environments, I guess, can be a challenge.
Yeah, so I mean, some of the coastal zone scanners have got very high spectral resolution, which helps a bit in that. It doesn't help with the spatial resolution, but understanding what the surfaces are covered with is getting better, I think, all the time.
Thank you. Turning to you, John, I'm just going to dive in now and ask you to just explain how climate change is affecting Antarctica. Just give us an overview of the state of Antarctica at the moment and the impacts of climate change.
It's interesting that we know that the polar regions are likely to be one of the first parts of the planet to respond to climate change, but the change that we've seen in the Antarctic is so far a lot less obvious than the changes we've seen in the north, in the Arctic. But there are clear signs of impacts on the Antarctic, and particularly if we look at the amount of ice in the Antarctic, we can now map that using satellite, and we are seeing quite large losses of ice from parts of the Antarctic, not all, but particularly the West Antarctic.
Before getting further into the question about what's going on in the Antarctic, you talked about the fact that there's this difference between the two poles in terms of our current understanding of their response to climate change. Can you explain why we are seeing that difference?
It's quite complex, but if you want a sort of simple 30-second view, you can describe the Arctic as a frozen ocean surrounded by continents, and the Antarctic as a frozen continent surrounded by an ocean which freezes partly during the winter. The Antarctic is in many ways isolated from lower latitudes because we don't have continental land masses extending far to the south, and so we're able to get continuous ocean currents running around the Antarctic continent, winds blowing much more in a west to east direction than the more disturbed patterns that we see in the Arctic, which link the Arctic through to lower latitudes. So in a nutshell, that's why we wouldn't necessarily expect to see exactly the same kinds of changes in both regions.
Might it be the case that the drivers or the chain are in some sense the same? It's just that the Antarctic is less quick to respond. Or is that the wrong way of thinking about it?
In some ways, that is the case. The other big difference is that although we've got one big grounded ice sheet in the Arctic, that's the Greenland ice sheet, it's a lot smaller than the ice sheets that we have in the Antarctic, where you've got the whole of the continent covered in very thick ice, up to 4 kilometres deep in places. These two systems respond in very different ways to changing climate.
What I'm trying to get at, John, is the idea of tipping points. I think in to some extent in the wider public consciousness, the idea of a sort of tipping point reached when there's much less freezing of the North Pole is something that's kind of entered public consciousness. In terms of Antarctica, are there similar sort of tipping points that we should be aware of and concerned about?
I think an honest answer is that we don't really know. Whereas, as you say, in the Arctic, we've seen this very rapid decline in the sea ice cover in the Arctic Ocean during the summer. There are reasons to believe that we may already have passed a tipping point where it's inevitable that decline will continue, and it's to some extent irreversible under current conditions. There may be tipping points in the Antarctic system, but we're a lot less sure about them, and there's no clear evidence at the moment of being close to a tipping point.
So what is our sort of deeper understanding of the climate and the kind of the earth science of Antarctica? Are there some really big questions about what's going on, or is it just a sort of a lack of data to fill in the picture?
The Antarctic climate system is very, very complex because you've got these three major elements of it: the Southern Ocean and the sea ice that forms on the Southern Ocean at high latitudes. And then you've got the big ice sheets on the continent, and connecting these two, you've got the atmosphere. They're all coupled in quite complex ways, and on a whole variety of timescales. We're only just beginning to get the kind of modelling capability that we need to understand how that complex system is going to change over time. If you change the way it's being forced, there's still a lot we we don't know about it.
And how sort of integrated do you think the sort of the Antarctic system is to the sort of global climate? In other words, can we afford not to worry too much about what's going on in Antarctica, or do you suspect that that there'll be feedback between what's going on in Antarctica and the global climate?
No, it's a lot more strongly connected to the global system than might be apparent at first glance. There's very strong connections through the oceans that things going on close to Antarctica in the Southern Ocean drive major components of the global ocean circulation, particularly in the Atlantic Ocean. We see dense bottom waters being formed close to the Antarctic continent, and these flow right the way up through the Atlantic and are found way north of the equator. So what's happening in the Antarctic is a major driver of this great ocean conveyor belt, which moves heat around the climate system. Also, the great ice sheets that sit on the continent, if there's any change in the amount of ice there, then that impacts directly on global sea level. That doesn't remain in the Antarctic. It will come and hit us wherever we are.
And you're saying that we're starting to see sort of considerable ice loss from parts of Antarctica?
From the West Antarctic ice sheet in particular, and this is part of the Antarctic ice sheet that is sitting on land, which is actually below sea level. This makes it really quite sensitive to changes, and particularly if you're able to start melting it where it flows into the ocean at the edge of the continent, then because of the configuration that we've got with the ice sitting on land below sea level, it's quite possible once you start melting it, then you get accelerating melting taking place. So there's clear evidence of rapid loss of ice from the Antarctic ice sheets in this sector. Less so from the rest of Antarctica, but it's still probably a major contribution to sea level rise over the coming century.
And the knowledge we have about this, you mentioned satellites. That's an important part of how we know what's going on. What are the other techniques that you rely on to build up a picture of Antarctica and its relation to global climate?
Well, satellites observations have been particularly important for the Antarctic because our network of climate observing stations on the ground is very, very sparse, much sparser than we've got say, in Europe or North America, which makes understanding climate and climate change in the region very, very difficult. And since about 1980 or so, we've had satellite measurements which give us a really good picture of how the atmosphere is behaving. This isn't a long record in terms of global climate records, and we really do need to understand climate variability on longer timescales than this. So the network of observatories that we've got at scientific stations, largely around the coast of Antarctica and one or two inland locations like at the South Pole, are very, very important in providing a sort of baseline network of longer-term observations, but it's a very, very sparse network.
I'm just a question about the sort of the greenhouse gas emissions that are involved in doing the research. So getting sort of scientists and equipment from the UK to Antarctica must require quite a lot of fuel. How do you think about the balance between the emissions and that are needed to do that and the kind of knowledge that you generate from that research?
Well, there clearly are tensions there, and it's something that we're becoming increasingly concerned about, and looking at our carbon footprint and thinking about how we can minimize it, because obviously if we're communicating messages that we need to cut down on carbon emissions and we're not seem to be doing anything about it, then that's not going to go down well. We are a significant emitter of carbon through some of our activities. Probably operation of ships is our most carbon intensive activity. We are just in the process of retiring one research vessel that we operate, which is 25 years old, replacing it with the new Sir David Attenborough, which is a state-of-the-art modern ship, uses the most fuel-efficient technology available. There's all sorts of filters fitted to the engine exhaust to avoid introducing pollutants into the atmosphere. So through activities like that and through looking at the possibility of using renewable energy at our stations, we are taking steps to reduce our carbon footprint and hopefully setting an example.
Can I end with the final question, which is sort of about how you feel and think about the state of Antarctica and the state of the world? Because from our conversations, we understand that emissions and the kind of energy that's built up in the Earth system is going to take a long time to play out, even if we collectively manage to meet kind of the Paris commitments and act urgently to reduce emissions now. And of course, there's the worry of some of the tipping points you've mentioned. When you look into, decades and centuries into the future, how do you feel about where we are and where we're going?
A mixture of optimism and pessimism, I think. It's frustrating to see that changes in attitudes can only take place rather slowly. One would like things to be moving a lot faster. But when I look back over what's been achieved over the past few decades, I think there are grounds for optimism. I would never have imagined that the UK would be generating as a larger proportion of its electricity from renewable resources as it is now. So I think there are indications that change is possible. Obviously, we have to keep pushing to keep that change going as quickly as possible. But I'm not totally pessimistic about the future, but also being realistic. We have to recognise that we've pumped a lot of additional carbon into the atmosphere over the years, and that we are committed to considerable warming still, even if we stopped all carbon emissions tomorrow. So we're going to have to live with climate change. We're going to have to adapt to it to some extent, while at the same time cleaning up our act.
Thank you, Joanna, Penny and John, for joining us. We'll be off next week for our mid-season break, but we'll be back on April the 9th for the next episode in this mini-series, which will be exploring conservation efforts in Antarctica and in the deep ocean. This week, we're also marking the 1-year anniversary of the launch of CSaP's Science and Policy podcast. And I wanted to take a moment to thank all of you for listening and for sharing our show over the course of this first year, as we've explored topics including policymaking for pandemics, green recovery, new genetic technologies, and how we're interacting with and impacting on our planet's most extreme environments. If you've enjoyed listening to our show, please do spread the word. We'd appreciate it if you shared an episode with a friend or rated us on your favourite podcatcher. Thanks so much for listening. CSaP's Science and Policy podcast is a production of the Centre for Science and Policy at the University of Cambridge. The series is hosted by me, Rob Doubleday, and is produced by the fabulous Kate McNeil, with the excellent support of 2 PhD interns, Alice Millington and Anthony Lindley. You can learn more about CSaP's work by visiting us on Twitter at CSciPol or visiting our website www.csap.cam.ac.uk. If you have any feedback about this episode or ideas for issues we could explore in future episodes, please email us at inquiries@csap.cam.ac.uk. Thanks for listening.